Welcome to video 4 on the TTb course. This video is from part 2 of the course. In part 2, from video 3 to video 10, we consider various techniques that form the foundation of reliable TT systems. In this video, we're going to consider techniques for storing data in tasks. We will also begin to consider techniques for transferring data between tasks. The material in this video is based on Chapter 4 of the ERES2 book. If you haven't yet read Chapter 4, I suggest you stop the video now and read Chapter 4 before you continue. We talked about this example first in video 1, when we discussed and introduced the concept of freedom from interference, or FFI. So in video 1 I suggested that this might be an ideal view of the world. We might have a scheduler in our system running on one processor, task A in our system running on a different processor, task B in our system also running on a separate processor. 3 processors in total. In this way, I suggested it would be easier to ensure that task A couldn't interfere with task B, and that task A, for example, couldn't interfere with the scheduler in an unintended manner. Of course, for most designs, this multiprocessor implementation would be rather impractical. Instead, in the real world, we have a situation that looks a little more like this. We're going to have a single processor typically, and we will have multiple tasks running on that processor supported by a single scheduler. This situation is a little more challenging to work with. In any non-trivial embedded system, there are a great many ways in which it's possible for tasks and other software components, such as a code library, that share the CPU and memory and other resources to interact. So these various software components can interact if we're not careful. So, for example, if we have an array of 30 elements and we write to element 40 in our array, and we haven't checked this, we'll be writing to an area of memory that we shouldn't be writing to, and this may have an impact. This area of memory may be used by a variable in a separate task, and that variable value could be corrupted. Because of the possible interaction between tasks and schedulers in this kind of design, any claim that we can prevent unintended interference between tasks would be difficult to guarantee. And in general, I would suggest you should be skeptical if someone tells you that you can guarantee that one task won't interfere with another task, for example. This doesn't mean that we need to dismiss a claim or an intention or a goal of freedom from interference in our system as unachievable, because that's not necessarily the case. It may not be possible for us to prevent any possible interference between tasks, but it may be possible to detect such interference if we build our system in an appropriate way. One key goal of the techniques that are presented in this course is to enable developers to provide evidence of the circumstances in which it will be possible to detect interference between tasks or between tasks and the scheduler and vice versa on a given processor, and to provide evidence that the processor will, for example, be able to move into a fail-safe processor state or a limp home processor state as appropriate for the application in the event that such interference is detected. In this video, we will begin to explore ways in which our decisions about methods for storing information in tasks and for transferring information between tasks can have an impact on our ability to detect the impact of interference from various sources on our system. Let's look briefly at an example. What this slide is supposed to suggest is that we have 5 tasks, A, B, C, D, and E. task A, task C, and task E are exchanging data by means of variable X. Let's just assume this is a global variable. So it's a processor global variable in this case. And it's accessible in effect to all of the tasks that operate on this processor. Only task A, task C, and task E are intended to be able to change the value of that variable. But it's possible, because it's a global variable, that task B or task D could also inadvertently or maliciously change the value of variable X. It's also possible that an unknown source could change the value of variable X. For example, some part of a code library that's running our system, a third-party code library that we may not have checked correctly, could also change the value of variable X. Or electromagnetic interference or radiation could cause a bit flip in memory and could again change the value of variable X. Using the techniques that we're going to discuss in this video, we should, in most circumstances, be able to detect such changes. We should be able to detect unintended changes to the value of variable X and other variables that are used in our system. We're going to work with a technique that we call duplicated variables. It's a very simple but highly effective way in which we can detect unintended changes to the values of variables that are used in our system. This is all we need to do. We store 2 copies of all long-term data. Please look up the definition of long-term data in Appendix 1 of the ERES2 book. We're going to store 2 copies of all long-term data. We're going to check the integrity of the data every time they are used, and we're going to decide what to do if we detect data corruption. We'll consider the use of duplicated variables over the course of the next few slides. What we will do in a duplicated variable is we'll store 1 normal copy and 1 bitwise inverted copy of each variable. So here, for example, we have a module global variable, data G, and it has a value of 1, 2, 3, 4, and we're storing an inverted copy of that variable, data IG, and I'll use this notation in all the various examples, I for inverted copy, and that's set to have an inverted copy of the value of the data that are stored in data G. This is standard C code. By storing an inverted copy rather than simply a copy, we reduce the chances that a block of memory that has been erased, or where all memory locations have been set to the same value, will be seen as containing valid data. So for example, if we set our data up like this and inadvertently erase the memory, then we won't have an inverted copy of data G. So data G will be set to 0, but data IG will also be set to 0, and the first time we check to see whether data IG is an inverted copy of the value of data G, we'll find that that is not the case, and we'll detect the memory corruption. We usually aim to check the integrity of duplicated variables every time we use the variable. So here's a simple example. Before we use left actuator enable variable, we check that it is an inverted copy, is correctly matched to its inverted copy. If it's not matched, the duplicate value has been corrupted. So we aim to check the data integrity every time we use a duplicated variable. As a default position, we typically start the design by assuming that if we detect corruption in a duplicated variable, we will shut down the processor in which the problem is detected. So that will be our default behavior. in the examples on this course. So here is an example of how we might achieve that. We find data corruption here. We're just about to use this variable. We find the value of the variable has been corrupted, and we're going to perform a safe shutdown of this processor. We'll talk about some other options that we can consider later in this video, but this is going to be our default position. So suppose we consider two examples. Suppose we're controlling a set of robots in a factory, and these robots might be used to manufacture a passenger car, for example. We've got a set of robots in a factory. We detect data corruption, not necessarily particularly surprising. These robots may be carrying out arc welding. It may be a high EMI environment, but we detect data corruption here in our duplicated variables. We can safely shut down the system, probably. So we shut down the system to avoid any potential damage resulting to workers in the factory, people around the robots, if the robots do not behave as expected. In the second situation below here, if we detect data corruption in this situation, simply shutting the vehicle down would clearly, not necessarily, be a sensible option. If your car stops in the middle of a level crossing and you're hit by a train, that's not an ideal outcome. So typically in this kind of scenario, if we detect a problem in the control system for the vehicle, we would want to enable not an immediate shutdown, but some kind of recovery option, including some kind of limp home option. So if the vehicle control system is not operating correctly, we might wish to allow the vehicle to continue moving, but restrict the speed to 10 or 20 miles per hour or 30 kilometers an hour, something of this order. So that the vehicle can still be moved to a safe location, but it cannot be used normally. So if we can't shut our system down safely, these are some of the options that we might wish to consider. We can perform a same mode reset. So we can reset the processor and restart it in the same operating mode. If the problem is transitory, for example, if it was caused by a bit flip in memory that was the result of electromagnetic interference, then this may address the problem. We'll say more about this kind of same mode reset in video 8. Generally, this is a very useful approach. Another thing we can consider if we detect a problem in a particular task is that we can consider replacing the task with a backup task. We'll discuss techniques for using backup tasks in video 6. Another option that we can consider as an alternative to shutting the processor down is to move the processor into a limp home processor mode. This would be the kind of behavior that we might require for the automotive example that we've just looked at. We'll discuss techniques for implementing limp home modes in video 8 on this course. These are of course simply design options that are available to you. Selecting the most appropriate solution will always depend on the particular system requirements that you face. What we're trying to do on this course is to present you with a range of design options. You can think of them as design patterns that you can select from to implement an appropriate solution for a particular system. So in this course, we recommend that duplicated variables are used to implement static variables, module global variables, processor global variables, register variables, and reset variables. I'm not going to give you a definition of all of these terms here. It makes more sense to see these written down. You'll find definitions for all of these terms in Appendix 1 of the ERES2 book. say more about the recommendation that duplicated variables are used in all of these cases in this video and in video 6. So let's look at how this translates into a slightly more practical example. In video 2, we looked at a simple design in which we had a processor with a flashing LED and a push button input. When we pressed the push button, we stopped flashing the LED. When we released the push button, the LED started flashing again. And we used simple code like this to provide information about the current state of the switch from the switch module to other modules in the system. So the heartbeat LED task, for example, would obtain information about the current state of the switch by making use of this switch button get state function call. So in this case, all we did was we returned the value of a module global variable using the getState function. That was from TTRD202A that we discussed in video 2. This is from TTRD04A. This has similar behavior, but now we are using both switch button pressed G and switch button pressed IG. So we've duplicated the switch button pressed variable. And now every time we return the switch state, we're checking the integrity of this duplicated variable. And in this case, we're performing a system shutdown if we've detected corruption in that variable. If we don't detect such corruption, we're returning the state of the variable. As we discussed in the last few slides, you may not wish to perform an immediate system shutdown. The code can be adapted to meet those requirements, but our default behavior here is to assume that we'll perform a shutdown of a particular processor if we detect corruption of a duplicated variable. You may like to take a look at TTRD204A. This code is publicly available on our website to see the rest of the details of this example. Go back. So in this case, we're talking about task data. The second main component we have to consider is the scheduler data. So suppose one of the tasks or some form of external interference corrupts the scheduler data. This could have very, very serious consequences. If we corrupt the data array that we first looked at in video 2, we could end up running the wrong task or running tasks out of sequence or simply triggering a task at the wrong time. And this could have very serious implications. For example, we might have code in our system that releases an airbag. If we release the airbag at the wrong time, this could clearly have very serious consequences. So one of the things we want to do is ensure that we protect the scheduler data, and we'll do that using duplicated variables. We can then check the integrity of these data at every tick. Again, TTRD204A illustrates this process. So this is the timer ISR, the scheduler interrupt function from the TTRD204A. So we're keeping a record of the tick count variable. So our tick count variable is now duplicated. And if we detect corruption in this tick count variable, as you would expect by now, we perform a shutdown. We're also continuing the same checks that we carried out before, so we view these as precondition checks. If that variable is corrupted, we don't know what's happening to the system. The only thing we can do here safely, we are assuming, is shut the system down. If we pass these preconditions, we still have the other checks to perform. So in this case, we're checking to see whether the tick count has exceeded the tick count limit. If it has, this suggests that one or more tasks has taken too long to complete. So we've had a task overrun situation. Again, we're treating this as a fatal platform failure. And again, a fatal platform failure is a defined term. So you'll find the definition of that term in the back of ERES 2 in Appendix 1. So we're treating the processor performs safe shutdown as a fatal platform. We're treating, the tick count G exceeding the limit and a task overrun as a fatal platform failure. If we've got this far, then we're updating our inverted copy of the tick count variable. So this is what happens in the scheduler ISR. Then we have the dispatcher function. So under normal circumstances, as you'll remember, the timer ISR, the scheduler ISR is triggered and immediately followed by the scheduler dispatch tasks function. So we've already checked the integrity of the tick count variable in the timer ISR. We don't need to check that again. But what we are checking here is we're checking the integrity of all the data used for the scheduler. So we're checking the function pointer for each task in the scheduler array every time we call this. We're checking the function pointer has not been corrupted, we're checking the delay value, and we're checking the period value. So we're storing each of these as duplicated variables, and we're checking these every time we have a scheduler tick. This is fundamentally important because if there has been corruption, we want to detect that before we release any tasks. So we talked about using duplicated variables to protect data in the tasks and to check the data integrity of data in our tasks and to check the data integrity of data used in the scheduler. In this course, we take the view that duplication of return values from functions and function parameters is not necessary, because the opportunities for interference during such a transfer in the type of TT system that we're discussing in this course are very limited. So we're not suggesting that it's necessary to duplicate all function parameters, and we're not suggesting that it's necessary to duplicate return values from functions. Of course, you may choose to have make a different decision about this, and you may have company coding guidelines that require you to duplicate these variables too. That's fine. It won't do any harm. Next question we have to think about are constants. Quite often people use code like this, and I've used code like this myself. Switch pressed we're going to define as a constant of 1, switch not pressed we're going to define as a constant of 0. But if we assign these values to a variable and we have a single bit flip in memory, it's possible that switch pressed and switch not pressed could be confused. So we suggest on this course that you use some alternative values. So rather than using switch pressed of 1 and switch not pressed in this way, use values that are less easily confused. So we've got some inverted copies here, and in general we would detect even a single bit flip in memory if we use these values appropriately. And there are various examples that we'll see during the course of the remaining videos on this course. Two other forms of duplicated variable are used in the various designs presented in this course. Register variables store a copy of a register configuration. Reset variables can be accessed by tasks or functions in more than one system execution on the same processor. For example, we might store the data, reset the system, and read the data after the system restarts. So we'll use register variables. We'll use register variables to support our interaction with peripherals in video 5. We will use reset variables to support reset-based mode changes in our discussions in video 8. So we'll say more about these shortly. I won't say anything more about register variables or reset variables in this video. There are, of course, alternatives to the use of duplicated variables. I want to look at some alternatives to the use of duplicated variables over the course of the next few slides. One of the main suggestions that people make when I discuss the use of duplicated variables with them is, we don't need duplicated variables, we have a memory protection unit in our microcontroller. And that's certainly something that is worth considering. So typically an MPU allows the programmer to indicate at specific times during the program execution that memory locations must not be accessed. So if an attempt is made to access these protected locations, the access is prevented and a fault is signaled, usually by triggering an interrupt. This can be a useful contribution to the design. However, there are several issues that can arise when a memory protection unit is employed. One key challenge with an MPU is that we can't, in current hardware at least, allocate, say, 3 bytes of memory for the exclusive use of task X and another 4 bytes of memory for the exclusive use of task Y. The control of memory is usually rather less fine-grained than this. We might still decide that use of a memory protection unit would provide a means of protecting the scheduler data, which is usually in a larger block. And you can sometimes do this effectively. So we can do this by ensuring that every time a task is released, the area of memory in which the scheduler data are stored is protected. Once the task completes, the protection is removed, allowing the scheduler to operate normally. This can be an effective solution. If you'd like to see an implementation of that, have a look at the first edition of the ERES-1 book. You can download that first edition from our website. So we can run a scheduler effectively in this way. Effectively provide memory protection for the scheduler data while a task is running, remove that protection when the scheduler updates, reapply the protection when you release the next task. However, one challenge with this is it can be challenging to support periodic checks of memory, a key requirement in many systems, in systems that employ an MPU. We would usually wish to use a task to perform periodic memory checks, and this task is going to require access to the area of memory in which the scheduler data are stored. If you provide access for the memory checking task, then it's more difficult to be sure that other tasks will not obtain such access too. Another issue with MPUs is that these mechanisms are seen by a magical cure, a panacea, a cure-all by some designers. This is rather like watchdogs. People think that an MPU is a cure for all design issues that might be associated with memory corruption. This can be very dangerous. If you consider, for example, the possible impact of EMI on memory contents, a memory protection unit will not address this. The kind of techniques we've been using with duplicated variables will detect such corruption. If you wish to use an MPU, we suggest you use duplicated variables too. Suppose we're transmitting data between tasks on the same processor. We require a mechanism that will usually be used with small blocks of data, for example an integer. The tasks may be released many times a second. Using duplicated variables imposes a low processor load, and modern processors will usually have sufficient memory to support this kind of checking mechanism. Suppose we're transferring data between tasks on different microcontrollers. Typically, we will be transferring larger blocks of data, for example 100 bytes at a time. The message transmissions are likely to be comparatively infrequent when we compare with data access on the processor itself. If we're sending 100 bytes of message and we try and use duplicated variables, the message size will be doubled. This may well be impractical. We will usually therefore employ distributed variables in a multiprocessor design. Distributed variables are not duplicated. Instead, they're usually protected by means of a CRC code and sometimes a sequence number. Suppose we have a 100-byte message. We may have to add only a 4-byte CRC calculation, the results of a CRC calculation, to obtain a similar level of protection to that obtained using duplicated variables. The CRC calculation will usually employ hardware support to reduce the processor requirements. You'll find a definition of distributed variables in Appendix 1 of the ERES2 book. We'll say more about distributed variables in video 9. There's another way in which we can duplicate our variables. We can run similar code on two different processors at the same time and perform cross-checks between the two different software versions. Such a solution is referred to as a duplicator platform in this course. We'll discuss this architecture in video 21. It can be an effective solution in some cases. Working with diverse tasks can also be useful, and it may offer an alternative to the use of duplicated variables. Suppose, for example, we run two slightly different versions of task X in sequence, and then we only take action if the two implementations agree. So we perform the same calculation, essentially the same calculation, using two different algorithms. So we run task X1 followed by task X2 using different algorithms in each version of task X, and we only take action, we only lower the undercarriage in our aircraft if the two implementations agree. We use such an approach in a decompositor platform. We'll discuss this option in video 21. We'll talk about the design of diverse tasks in video 6. Again, you'll find a definition of diverse tasks in Appendix 1 of the ERES2 book. One final option we can think about. If we have duplicated data and we do a check of the data and find that the two data values don't match up, then all we can tell is that the data values have been corrupted. There's nothing much we can do. We don't know which of the two values is correct. Suppose we don't duplicate the data. Suppose we triplicate the data. If we then find that 2 values out of 3 are the same, we can correct the third value, the value that doesn't match the other two, record the fact that a discrepancy was detected, and carry on with the system operation. Provided we don't get, say, more than 2 discrepancies per hour, we might be happy that the system will continue to operate correctly. This kind of approach can work, and it's employed to scrub memory in some space systems where memory upsets are expected to occur. For the majority of designs, the overheads and complexity involved in storing and processing the triplicated data are difficult to justify, and we won't use triplicated data on this course. That brings us to the end of this video. Before you watch the next video, please read Chapter 5 in the ERES2 book. Thank you for watching this video.